Sound check, sound check. Chemistry, we're moving on to the third lesson in our unit on intermolecular forces, and this deals with phase diagrams. Okay, so there are three states of matter: solids, liquids, and gases. So a phase diagram shows the state of a substance at a combination of temperature and pressure. So we've talked about that intermolecular forces are such that when you put a high temperature into molecules, they want to break apart. They'll also break apart if you lower the pressure because there's not as much atmospheric pressure pushing down on them. Think of water in a glass, and so they can more easily escape. So molecules tend to want to come apart and form gases when there's high temperature and low pressure. The other direction, they tend to want to form solids when the temperature is very low. You take the energy out of them, so they want to stick together. The Coulombic forces are dominant then, and they stick together. Or when you put a lot of pressure on them, high pressure, you squeeze them together, you push them together. So the phase diagram shows the combination of temperatures and pressures at which substances exist as either a solid, liquid, or gas. So you see over in the far left, you have low temperature and a range of pressures there, but at very low temperatures, they're going to be solids. At a middle range of temperature and a middle range of pressures, they're going to be liquids. And if you get up to high temperatures or very low pressures, then they will become in gas or vapor form. Now you can see there the transition between phases have names. Some of the names you're very familiar with, some of them not so much. So if we look at going from solid to liquid, think of water. If water goes from solid, that's ice, to liquid, that's called melting. If it goes from liquid to solid, that is turns to ice, that's called freezing. Now if you go over to the line between liquid and gas, if the liquid becomes a gas, then we think of it as evaporation, but that's called vaporization. If it goes in the other direction, it's called condensation, going from gaseous water vapor back to liquid. That's what you see in the morning on plants and on car windshields, is that condensation of liquids. And then the two that are a little bit less known are going directly from solid to gas, because that's somewhat unusual. In other words, you're going from solid to gas without going through a liquid phase, and that's called sublimation. If you go in the other direction from gas directly to solid without going through a liquid phase, that's called deposition. Now there's a very specific point where a substance exists as a solid, liquid, and gas all at the same pressure at the same time. And that point is called the triple point. So it's kind of the borderline between all three of the states of matter. Okay, the critical point is the highest temperature at which a substance can remain as either a liquid or a gas. At that point, it just becomes a mixture of the two, and that's above the critical point. The names given to phase changes are shown in the phase diagram, and we just went through those. So for all substances, if we hold the temperature at T2, so look at T2 over there on the temperature axis, and increase the pressure from C to D, the substance will condense from gas to liquid. So we've talked about that you can get a substance to go from vapor down to a liquid by squeezing the molecules together, just squeezing them, physically squeezing them together into a liquid. For most substances, if we hold the temperature at T1 and increase the pressure from A to B, the substance will freeze from liquid to solid. So again, you're squeezing the molecules together, So instead of becoming loose where they can move around each other, which is what a liquid is, you're squeezing them tight together so they're in fixed positions, which is what a solid is. And this is true for most substances. So you'll notice that line right next to where the B is sloping to the right. And that will happen for most substances. As you increase the pressure, you will turn them from a liquid, you'll squeeze the molecules tighter together, and they'll become a solid. Higher pressure squeezes molecules into a tighter position and creates a solid. That's from A to B. The critical point of a phase diagram is the pressure and temperature at which the gas and liquid phases cannot be distinguished from each other. So you're getting up into very high pressures and very high temperatures. Critical temperature is the highest temperature at which a liquid can exist. So when you go above the critical temperature, it's going to be a gas at any pressure, no matter how high or low the pressure is. The triple point is the pressure and temperature at which the substance exists as a solid, liquid, and gas all at the same time. Molecules with high intermolecular forces are either highly polar or they're large nonpolar, large LDF, London dispersion forces molecules. They stick together better, so they have higher critical temperatures than smaller nonpolar molecules. So highly polar and large nonpolar have higher boiling points than weakly polar or small nonpolar. So compare the phase diagrams of H2O, water, and carbon dioxide. So carbon dioxide is on the left, water, H2O, is on the right. At normal room temperature, that's about 300 degrees Kelvin and a pressure of 1 atmosphere, and that's shown at point X on each of those two phase diagrams. So water is a liquid and carbon dioxide is a gas. So if you see that carbon dioxide is down, so that red line represents 1 atmosphere, and where the X is right around at 300 degrees, so that's going to be a gas for carbon dioxide. But for water, if you look where it is, again, the red line is at 1 atmosphere pressure, normal air pressure, and again, the X lines up with a temperature of right around 300 degrees, so you can see it's in the liquid phase for water. So at normal room temperature and pressure conditions, carbon dioxide is a gas, water is a liquid. So solid water, ice molecules, are held farther apart by hydrogen bonds. Liquid water molecules are freer to move around and stay closer to one another. This means that ice is less dense than water. In other words, you have fewer molecules in a certain volume when you have ice than you do when you have water. In water, you have more molecules in that same volume, that same amount of space. So there you see ice, you see how it's hydrogen bonding, they're kind of pushing, the water molecules are kind of pushing apart. And there's liquid water where they're free to kind of move around each other. They stay in touch with each other, but they freely move around each other. And you can see how they're a lot closer together there. Solid water molecules form hexagonal structures where there's a lot of space between molecules. This makes ice less dense than water. So water is less dense in solid form ice than in liquid form. This means ice will float on top of liquid water. This is a rare feature in a substance. So you've seen this diagram before. There's water vapor, it's in gas, the molecules are completely separated. There's liquid water. You can see the dashed lines there. There are bonds. There's 2 types of bonds, or 3 types of intermolecular forces. There's London dispersion forces, but they're very weak and they don't really play a role in the intermolecular forces of water. They exist, but they're just not that important. Then you have the dipole-dipole interactions between the positive and negative sides of one water molecule to another, and then you have the hydrogen bonds. But since the water can move around, it will break the hydrogen bonds fairly quickly because the water can slosh around. So this is, if you lower the temperature and take the pressure off the water molecules, in other words, you don't squeeze on them as tightly, they can stretch out and form this kind of pretty hexagonal structure, and that's the structure of water molecules in an ice cube. if the temperature is held at T1, so you look down at the bottom, there's T1, and the pressure is increased from A to B, then water will go from a solid to a liquid. This is different than most substances. So think about that. This happens. Notice that that line between A and B, where that red dashed line is passing through, the one between water and ice, notice that it's sloping to the left. That's different than the phase diagram, than most phase diagrams. So why does that happen? What does that backwards or leftward sloping line between ice and water mean? It means at lower pressure, water will be at lower pressure at a given temperature, so you keep the temperature the same. At lower pressure, the water will be ice. It'll be solid. Why? Because at low pressure, the molecules can stretch out into hydrogen bonds, and that's what you saw in the last slide. Now, as you increase the pressure, what you do is you squeeze the molecules together. You crush those hydrogen bonds. And so at higher pressure, it turns into liquid water. Again, this is the opposite of most substances. Most substances, if it's at low pressure, they'll be kind of loose and they can flow around. And at higher pressure, they'll squeeze together into a solid. And they're squeezed in very rigid positions. But with water, it's just the opposite. And that's because of the hydrogen bonding. So be sure you can explain that. So again, water is unusual because at low pressure, it can create the hydrogen bonds and stretch out into those hexagonal structures you saw on the previous slide at low pressure. At high pressure, you start to squeeze those hydrogen bonds and you crush them, and the water molecules fall together into liquid form. And so that's why this line between ice and water is backward sloping. Lower pressure is the solid, higher pressure is the liquid water. That's very unusual in most substances. So water has a backward sloping curve between solid ice and liquid water. This is very unusual. So high pressure pushes water molecules closer together. Liquid water molecules are closer together, so high pressure creates liquid water. And you just have to go back to that previous slide and see what the liquid looked like compared to ice. Low pressure allows the water molecules to spread out and create hydrogen bonds. So low pressure creates solid water, which is ice. So there you see that diagram down at the bottom. When they get crushed together through high pressure, that would be point B. Then they just kind of look like a scramble. They look like a jumble there, and they're squeezed tightly together. When you take the pressure off, they can spread at the same temperature. You take the pressure off, they can spread out into the hydrogen bonds, and therefore they become less dense. You have fewer water molecules in the same amount of volume. So at higher pressure, that's B, water molecules are crushed together and are attracted to each other mostly by dipole-dipole bonds. At lower pressures, that's A, the water molecules are not crushed together and can stretch out to form hydrogen bonds that allow water to form hexagonal ice crystals. So this explains why water has a backward negative sloping fusion curve, and that's very unusual. The boiling point of a liquid occurs when vapor pressure equals atmospheric pressure pushing on the surface of the liquid. So you have atmosphere pushing down on the top of a pan of water. The water wants to push up, or some of those water molecules want to escape. So when the energy in the water molecules in the pan is enough to allow them to overcome the vapor pressure pushing down, then the water will start to boil. The normal boiling point is the boiling of a liquid at 1 atmosphere. That's at sea level. So at sea level, water at 1 atmosphere pressure boils at 100 degrees centigrade. In cooking, the water holds heat, which cooks food. So that means the water can get up to 100 degrees worth of kinetic energy of the molecules at sea level. Above sea level in the mountains, the pressure is less than 1 atmosphere, and water boils at a lower temperature. This means that the food takes longer to cook. So in other words, once the water gets up to say 95 degrees in the mountains, it's going to start to boil away. So it's not going to stay in the pan to put energy into the hot dogs to cook the hot dogs once it hits 95 degrees. That means the water in the pan that you're cooking the hot dogs can never get any hotter than 95 degrees. Therefore, it's going to take longer for the hot dogs to cook up in the mountains. Okay, so when the number of molecules leaving and re-entering the liquid is equal, they are in dynamic equilibrium, and the pressure they create above the liquid is the vapor pressure. Vapor pressure exists when liquid molecules gain enough kinetic energy to break free and exist in the atmosphere above the liquid, creating pressure. Some of the vaporized molecules will return to the liquid. So when the same number going back in equals the number coming out, that's called dynamic equilibrium. It means it's equal, but they're still moving back and forth between above the water and into the water. Since hot water has greater kinetic energy than cold water, hot water has greater vapor pressure. Okay, so that takes care of our lesson on phase diagrams, and we'll get into one more lesson on heating curves in the next lesson.